Hello, students. Have you ever played with a magnet and a paper clip? You know how the magnet can pull the clip towards itself without even touching it? It seems like magic, doesn't it? But really, it is just pure science. So today, we are going to explore this invisible world of magnetism, and I will show you how we can actually see these mysterious forces at work. Let's begin our lesson. So here is our plan for today. First, we will talk about this invisible force of magnetism. Then we will learn about a very important and accidental discovery. After that, we will learn how to visualize this magnetic field and what are the rules that these field lines follow. And finally, we will have a small checklist for your exams. I am sure all of you have played with magnets at some point. You must have felt that strange, invisible pull when you bring a magnet close to a refrigerator door, or maybe some iron pins. The pin just moves on its own. How does this happen? This invisible pull, this action at a distance, is the big mystery we are going to start with. Let's consider a simple compass. Why does its needle start moving or deflecting when you bring a bar magnet near it? Well, the secret is that the compass needle itself is a tiny little magnet. Yes, it's a small bar magnet that is free to rotate, and it has its own north and south pole. And you already know that a north pole will be pushed away by another north pole and pulled towards a south pole. It is this simple push and pull that makes the compass needle move. Now, for a very long time, scientists believed that electricity and magnetism were two completely different things, two separate forces. But all of that changed in the year 1820. And it was because of a scientist named Hans Christian Ørsted, who made a discovery completely by accident. So just imagine this. Ørsted was giving a lecture. On his table, he had a copper wire connected to a battery, and right next to it was a magnetic compass. Now, when he switched on the circuit, an electric current started flowing through the wire. And suddenly, the compass needle, which was pointing north, just twitched and deflected. It moved even though there was no magnet anywhere near it. So, just think about what happened. What is the only thing that can make a compass needle move? It must be a magnetic force. And what was the new thing that Ørsted introduced in his experiment? It was the electric current. So the conclusion was very clear. A flowing electric current produces a magnetic effect around it. And just like that, electricity and magnetism were found to be connected. Okay, so this invisible region of influence around a magnet, or even around a current-carrying wire, this is what we need to study now. But how can we study something that we cannot see? Well, it turns out there are some very clever ways to make this invisible field show us its shape. And this region of influence has a proper name. We call it the magnetic field. To put it simply, it is the space or the region around a magnet where its magnetic force can be detected or felt. Now, it's very important to remember that this field is not a substance. You cannot touch it. It is just an invisible region of force. So, how can we actually see this field? There is a very simple and beautiful activity for this. First, you take a bar magnet and place it on a sheet of white paper. Then, you take some fine iron powder, we call them iron filings, and you sprinkle them all around the magnet. Now you just gently tap the paper. What do you think is going to happen? And you will see this. It's like magic. The iron filings will arrange themselves into this beautiful pattern of curved lines. You can see it here. You see, each tiny piece of iron acts like a mini compass. It aligns itself with the magnetic force. These lines that you see are what we call magnetic field lines, and they give us a perfect map of the invisible magnetic field. Now, if we want a more accurate way to draw these lines, we can use a plotting compass. It is very simple. You place the compass near the north pole of the magnet. You make a small dot where the north pole of the needle is pointing. Then you move the compass, placing its south pole on the dot you just made, and you mark the new position of the north pole. If you keep doing this dot to dot, you will trace out one complete magnetic field line, all the way from the north pole to the south pole. So now we know how to see the shape of the magnetic field. But these patterns are not random at all. They follow a very specific set of rules, or what we call properties. Understanding these properties is very, very important for your exams, so let's go through them one by one. All right, let's look at these properties carefully. The first one is about direction. By convention, we say that outside the magnet, the field lines start from the north pole and go towards the south pole, but they don't stop there. Inside the magnet, the direction is from south to north. This means they form complete, continuous, closed loops or curves. Now look near the ends of the magnet, near the poles. Can you see how the lines are very crowded? This closeness tells us that the magnetic field is strongest at the poles. Where the lines are far apart, the field is weaker. And finally, a very important property. Two field lines never, ever cross each other. We will see why in just a moment.
So, when we draw these lines, how do we know where to put the arrows? The rule is very simple. The direction of the magnetic field line at any point is taken to be the direction that the north pole of a compass would point if you placed it at that point. This is a very important convention that you must remember.
Now, let's go back to that last property. This is a very common reasoning-based question in your exams. Why can't two magnetic field lines ever intersect? Take a moment and think about it. What would happen if they did cross? Here is the simple reason. If two field lines were to cross at a point, it would mean that at that single point of intersection, the magnetic force is pointing in two different directions. So if we placed a compass there, its north pole would try to point in two directions at the same time. And that is, of course, physically impossible. A compass needle can only point in one single direction at any given time. We have learned a lot today. So to help you with your studies and to prepare for your exams, let's quickly summarize all the important points from this lesson. This is your exam checklist. So for your revision, please make sure you know these things. First, be clear about the definition of a magnetic field. Second, you must practice how to draw the field lines around a bar magnet. Third, be ready to list at least 3 properties of these magnetic field lines. And finally, make sure you can very clearly explain the reason why two field lines can never intersect each other. And we will end with one final thought today. Ørsted's accidental discovery showed us a hidden connection, an invisible force created by something as simple as an electric current. It makes you wonder, doesn't it? What other unseen forces and connections are there all around us, just waiting to be discovered? Thank you for your attention.